Right, thank you, Pete. So yeah, as Pete said, my name is Pieter Vermeesch. I'm a professor of geochronology at UCL. And in this presentation, I will explain to you what that means. So geochronology is the science and art of dating rocks using radiogenic isotopes, although there are also some other methods. Radioactivity is the main means by which we date geological processes today. Now, the ultimate goal of geochronology is to date geological processes, including the age of the Earth, and that's been a question that has fascinated people for a long time. Religious dogma places the age of the solar system of the universe anywhere between infinity and 6,000 years, which is a very wide range indeed. And the first serious scientific attempts to improve on those beliefs is due to this man here, Lord Kelvin, one of the most important physicists of the 19th century and the founding father of modern thermodynamics. So thermodynamics is the science of heat transport in solids and in gases, and Kelvin used that understanding to derive an estimate for the age of the Earth by combining two measurements with two assumptions. The measurements were thermal properties of the Earth. Kelvin lived in the 19th century when there were lots of coal mines in the United Kingdom, and miners, as they went down into the Earth's crust, noticed that temperature rises at the rate of about 20 to 30 degrees per kilometer. And this is the geothermal gradient. So that's the first measurement that went into Kelvin's calculations. The second measurement was the thermal conductivity, which people could also measure in the 19th century. It's a property of solids. Their ability to conduct heat could be measured in rocks at the surface and in the coal mines. So by taking these two numbers and combining that with two assumptions, he could calculate the age of the Earth. The two assumptions were first that the Earth, when it formed, was in an isothermal state, which means that the temperature in the core initially was the same as the temperature near the edges, near the surface. Second assumption was that the Earth was losing and has lost heat only by conduction. So it's a solid inside, and that facilitates the calculations of heat loss to space. Using these measurements and assumptions, Kelvin calculated that it would take somewhere between 40 million and 200 million years for the Earth to develop a geothermal gradient of about 30 degrees per kilometer in its outside. So that is a lot longer than the 6,000 years that people believed prior to Kelvin. But geologists such as Charles Darwin still thought this was not quite long enough. Darwin knew that evolution takes much longer to really result in the diversity of life that we find on the planet today. So he thought that the Earth should be at least one, maybe two orders of magnitude older than 40 million years. But he couldn't find any flaws or mistakes in Kelvin's calculations. That's because there were no mistakes in the calculations themselves. Nevertheless, Darwin was correct, and Kelvin's age estimate was an underestimate, was incorrect, not because his calculations were wrong, but because the assumptions were wrong. There are two facts about the Earth that Kelvin didn't know about, people didn't know about in the 19th century, and that kind of threw off his calculations. The first fact is that the Earth inside is not a solid. Over geologic timescales of millions of years, it behaves more like a fluid. The mantle of the Earth, the inside of the planet, moves at a rate of centimeters per year, and over millions of years, it results in a wholesale overturning of the interior of the planet. So it's a liquid that is thoroughly mixed, and mixing of fluids, convection, is a much more effective heat loss mechanism than conduction, and it results in the maintenance of this isothermal state for much longer than would be the case if only conduction were the mechanism at play. A second thing that Kelvin didn't know about in the 19th century was the existence of radioactivity. There are certain elements in rocks and minerals that are unstable and fall apart, producing radiation that heats the surrounding materials. Now, these radioactive elements, such as uranium, thorium, potassium, samarium, tend to be enriched in the crust of the Earth, the outer layers. And again, that results in the isothermal state of the planet being maintained much longer than would be the case if radioactivity did not exist. Now, this radioactivity turns out to be an excellent method. It provides us with a solution to the problem of dating geological processes. It allows us to create much more accurate dates for the age of the Earth and other things. So to explain how radioactivity works, in the next few slides, I will give you a brief primer on this subject. I'm not sure how many of you know about radioactivity. I'll put everybody on the same page. I will introduce a few equations. Geochronology, like any science, depends on mathematics. I promise the maths won't be too complicated, but after I've done that introduction, I will then proceed with geological case studies, which will apply these principles to real-world problems. All right, so what is radioactivity? Radioactivity is a property of the atomic nucleus. Atoms are made of clouds of electrons that surround a nucleus that contains protons and neutrons. The name of an atom is derived by or refers to the number of protons. For example, an atom that contains 6 protons is called a carbon atom. The number of protons equals the number of electrons in an atom, and it controls the chemical properties of that atom. Now, most carbon atoms that we find in our solar system today bind these 6 protons together with 6 neutrons. 6 plus 6 is 12. So this type of carbon atom is called a carbon-12 atom. But not all carbon atoms in the solar system contain 6 neutrons. A small percentage of carbon contains now 6 plus 7 neutrons. It's still a carbon atom because it still has 6 protons. It is chemically identical to carbon-12, but this carbon 6 plus 7, carbon-13, is a different isotope of carbon that has slightly different physical properties. Because carbon-13 is heavier than carbon-12, if you have CO2, for example, that is enriched in carbon-13, it will have a higher sublimation temperature than carbon-12 because it doesn't evaporate so easily. All right, so you can fit an additional neutron into the nucleus of a carbon-12 atom. If you want, you can add another neutron, producing 6 plus 8, carbon-14, a third isotope of carbon, but you can only put so many neutrons into the nucleus of an atom. 8 is too many, and this form of carbon is no longer stable. It will fall apart, it will disintegrate, it will change into another form with time. In the case of carbon-14, carbon-14 will turn one of its neutrons into a proton. So we are going from 6 to 7 protons. The resulting atom is no longer a carbon atom, it is now a nitrogen atom with very different chemical properties than the carbon-14. In order to preserve charge, we have lost a neutral particle and gained a positive particle. In order to maintain charge, we must emit a negative charge, which comes in the form of an electron, which in the context of radioactivity is also called a beta ray. So this ray that is emitted by the carbon-14 atom is what gives radioactivity its name. And that can be detected with instruments such as a Geiger counter that I will talk about in a minute. So in the context of geochronology, the carbon-14 is called the radioactive parent, and the nitrogen-14 is called the radiogenic daughter. And this transformation of radioactive parents to radiogenic daughters forms the basis of geological clocks. Beta radiation is just one example of a variety of mechanisms that can turn one type of atom into another type of atom. Potassium 40, for example, is radioactive and changes to argon 40, not by emitting an electron, but by emitting a positron, which is essentially a positively charged electron. So instead of gaining a proton, we are losing a proton and gaining a neutron. Electron capture is another mechanism that randomly can affect other potassium 40 atoms, also produces argon 40, but instead of emitting a positron, as the name suggests, the electron capture will capture an electron from the electron cloud surrounding the potassium atom, incorporate it into one of its protons, turn that proton into a neutron, and also produce argon 40, not releasing a positron, but releasing an X-ray, a short wavelength photon. Alpha emission is a mechanism that affects heavier atoms, such as, for example, samarium-62, samarium-147, which has 62 protons, so it's much bigger than potassium or carbon, and changes to the lighter neodymium-143 by emitting 2 protons and 2 neutrons, which together form the nucleus of a helium atom. So these are called alpha particles. If alpha particles acquire electrons, they turn into helium atoms. And then finally, a fifth mechanism that we will discuss today affects a small minority of the uranium-238 atoms in the universe. Uranium tends to decay to lead and helium by emitting alpha particles, but once every 2 million times, uranium can also undergo spontaneous fission. Uranium-238 is the only isotope in the solar system today that undergoes this process. It's a violent process that produces 2 particles of roughly equal size. So the uranium loses a lot of neutrons, a lot of protons to achieve a stable state. And in the first 100,000 years or so of the solar system, actually, there were other elements or isotopes that underwent spontaneous fission. Plutonium, for example, was around in the first few 100,000 years, but those are all extinct now. Uranium at the moment is the only atom that undergoes this process. So all these mechanisms and all these radioactive isotopes, the parents and daughters, can all be visualized and tabulated, not on the periodic table of elements, but on a chart of nuclides, which is shown at the bottom of the slide, which sets out the number of protons in each isotope against the number of neutrons. So all possible isotopes in the universe can be plotted on this diagram. The stable ones are represented by these black squares. Radioactivity is the process whereby unstable combinations of protons and neutrons move towards this region of stability, from hydrogen to uranium-200 or to lead-206, which is or 208, sorry, which is the heaviest stable isotope in the universe. Okay, so this radiation, the alpha, beta, and gamma rays, short wavelength photons that are emitted by radioactive parents as they decay to radiogenic daughters, can be detected with instruments like this, a Geiger Müller counter. It's a simple device that consists of a metal rod that sits inside a cylindrical tube at a high voltage. So any ionizing particle that enters this tube will cause or create a small spark and result in a count being registered on this gauge. If you look closely at the slide, you will see that the units are C per M, counts per minute. And this reading is proportional to the number of parent atoms. So dP is delta P, the difference in parents that occurs per difference in time. It's the number of parent atoms that change to daughter. Each one releases one or more rays of radioactivity, can be detected in the Geiger Müller counter. So the change of parents per change of time is proportional to the readings on this gauge. Now, it has been shown time and again in countless experiments that this rate of decay, the readings on this gauge, are proportional only to the amount of parent that is present under the detector. It doesn't matter what the pressure is, the temperature, or the chemical form in which, for example, the carbon-14 is found. The only thing that controls the reading on this gauge is how much of the radioactive parent is present under the detector. The constant of proportionality is referred to as lambda, is the decay constant, and is specific to different isotopes. Every radioactive isotope has its own characteristic lambda value. And we've got a negative sign in front of this lambda to express the fact that we are losing parent with time. We are not gaining it, we are only losing it. We're gaining daughter at the expense of the parent. So this equation, which has never been disproven, has been tested many times, is a differential equation. It shows the difference of parent per difference in time as a function of the amount of parent. I don't think many of you will have solved differential equations. I'm not sure even if it's in the A-level curriculum. So, but I will step you through the solution of this equation, because it's important. If we want to estimate T from the amount of P, then we must solve this equation. And I will do that by approximating this equation in small steps. So I am going to break down time. I will track the evolution of parent as a function of time for a hypothetical parent that exists in 100 units. It could be 100 atoms of P at the start of our numerical experiment, or it could be 100 trillion atoms. We begin with 100 units of P. Our decay constant here is 0.1, so 1 divided by 10. And we are going to track the evolution of the parent through time in steps of 1. So my question to you, which you can enter in the Q&A box and which Pete will read to me, is during the first time step, so at time 0, what is the rate at which we are losing parent as a function of time, given that we start with 100 units of P and that lambda is 0.1. It's a very simple question. As soon as somebody enters an answer, I will proceed.
Hi there. We got an early first attempt. 0 question mark.
Ah, thanks for trying, but that's not the right answer. So you need to use this equation, right? We've got the change of parent per change in time as a function of P and of lambda. T doesn't come into this equation. So there is no 0. We are multiplying 100 with 1 divided by 10, and we have a minus sign. So this is going to be minus 10. All right. So in our first step, did somebody enter that?
We had two folks came in just after that first one and got
excellent
the correct answer.
Good. Well, thanks for participating. So in the first step, between time 0 and time 1, we are losing 10 units of P, and so we will only have 90 units of P left. So we start off with 100 units. After one time step, we have dropped to 90 units. Now in the second step, how many units of P are we going to lose? P is no longer 100, right? It is now 90. So we do exactly the same as we did before. We're going to plug 90 into this equation. We multiply it with 0.1. This decay constant doesn't change through time. No matter how old an atom is, it doesn't know how old it is. It will decay at the same rate. So we've got 90 divided by 10 with a minus symbol. We're going to lose 9 items between step 1 and step 2. We're going to have 81 left after the second step. So if we continue this process, you can see that we create this exponential decay function. We start off with 100 and we are losing parent with time. But as we are losing parent, the rate at which we are losing it is also decreasing. So we are asymptotically approaching 0, but we're never actually ever getting there. So this exponential curve that you can see here is the solution to this differential equation. So differential equations are functions that have derivatives in them and that have a function as a solution. You don't have a number as a solution, you have a function as a solution. And the function that is the solution to this differential equation is an exponential function. So here is a general form of that solution. The amount of parent that survives in our radioactive material is given by the initial amount of parent, we call that P0, times this exponential factor, which has a decay constant in it and time. Now, one characteristic property of exponential decay functions is that there is a characteristic timescale called the half-life that describes how long it takes for P0 to reduce to P0 divided by 2, and for P0 divided by 2 to reduce to P0 divided by 4, P0 divided by 4 to reduce to P0 divided by 8, and so forth. There's a one-to-one correspondence or relationship between the half-life and the decay constant. The half-life is easier to relate to because it has units of time. The decay constant has units of time to the -1, which is not so intuitive. So people tend to think in terms of half-lives instead of decay constants. And here is a table of some commonly used parent-daughter pairs and their respective half-lives. So carbon-14 decays to nitrogen-14 with a half-life of 5,730 years. And this may sound like a long time to you, but to geologists, it's not very long. Now, geochronometers do not go back. We can't go back further than about 10 half-lives. After 10 half-lives, there is so little parent left that we cannot measure it reliably. So radiocarbon only allows us to go back about 50,000 years. It's useful for archaeologists. It's not useful for geologists. We are interested in millions to billions of years. So we need to use different parent-daughter pairs. And this table shows 3 examples of those. Uranium-235 decays to lead-207 with a half-life of 700 million years. So uranium-235 is a survivor from the formation of the solar system and is still decaying to lead. Uranium-238 is a second isotope of uranium that decays to a second isotope of lead. So we get 2 clocks for the price of 1, and that is one of the great features of the uranium-lead clock. This is the reason why this clock is the most popular and powerful one in the geochronological toolbox. Uranium-238 decays to lead-206 with a half-life of nearly 4.5 billion years. And then rubidium-87 decays to strontium-87 with a half-life of nearly 50 billion years. So there is a very wide range in decay constants, and these guys here allow us to date geological processes anywhere between 1 million years and about 4 or 5 billion years, even older, but of course the solar system is not older than that. So how do we use these very slowly decaying, barely radioactive elements? If you put a Geiger counter over some uranium, you are barely going to detect any radioactivity. It's so, the level of radioactivity is so low that you can not really use it for geochronology in that way. Another problem is that we have no idea how much parent was initially present in our sample just by measuring how much parent is present in it today. But there's a clever trick that geochronologists use that allow us to solve this equation for both P0 and time, which is the quantity that we are interested in. Even though we don't know how much parent was present in our sample today, we do know that any parent that has decayed since the crystal formed, since the material achieved isotopic closure, is still present in our sample as a daughter. So if you take the sum of the daughter atoms that are present in the sample plus the surviving parent atoms, the sum of those two should equal the amount of parent that was initially present in our sample. Now, these are all measurable, detectable quantities. So we can rearrange this equation by bringing this exponent to the left-hand side, bringing the amount of parent, the number of parent atoms in the sample, to the right-hand side, taking logarithms of both ends, taking the lambda decay constant to the right-hand side, and we get an equation for time, which is a function of the decay constant, which we know, and the ratio of the amount of parent to the amount of daughter to the amount of parent that is present in our sample today. And those ratios can be measured very accurately and very precisely using sophisticated machines called mass spectrometers, 3 of which are installed in my lab at UCL. So mass spectrometers come in many different sizes, shapes, and forms, and they can measure a wide range of these parent-daughter pairs. And there are many of these that are available in the geological toolbox, the geochronological toolbox, each with their own applications, their own strengths, and their own weaknesses. So in the next part of the presentation, I will walk you through 4 of these systems to highlight some of the applications of geochronology. So the first technique that I would like to discuss in a bit more detail is the uranium-lead method, which I already briefly mentioned before. Is based on the radioactive decay of uranium, the heaviest element in the solar system, in its most common isotope, uranium-238. It has 92 protons, that's why we call it uranium, and 146 neutrons. It's a really massive atom. It's essentially too big for its own good, and it will decay with time to smaller, more stable atoms, notably lead, as I explained before, and alpha particles, which, when they acquire electrons, turn into helium atoms. Uranium decays to 1 lead atom and 8 helium atoms. So we get 2 clocks for the price of 1. The uranium-lead clock, the ratio of lead to uranium, allows us to date the crystallization age of uranium-bearing minerals. The uranium-helium clocks tells us something different about our rock, but I will say more about that in the 5th segment of this presentation. Uranium-lead is a very powerful method to date the crystallization age of rocks that originally formed from magma, and any rocks that are then subsequently produced by the erosion of those magmas and preserved as sediments, or rocks that were initially crystallized from a magma, turn into sediments, then buried, melted again, and recycled in a new magma. So all these different processes can be dated with the uranium-lead method. So it has been very widely applied to rocks around the world, the oldest of which were found in Greenland. The oldest rock known to science on our planet is found in the Isua complex. It's 3.8 billion years old, which is very old indeed. And it's very badly deformed. So you can see that over this long and eventful history of this area, it has been caught up in several mountain building events, collisions of tectonic plates that have very strongly deformed the rocks. And this is one reason why no older rocks have been found. The Earth is a dynamic planet. Not only tectonics, but also weathering can destroy rocks and overprint overprint any geochronological signals frozen into them. So 3.8 billion years is 2 orders of magnitude older than Lord Kelvin's estimates. Charles Darwin would be happy with this date, but it's of course still not the age of the Earth. It's the oldest rock that we know. The Earth it's a minimum age estimate for our planet. The oldest material found on Earth is actually older than the oldest rock. It is found not in Greenland, but in Australia, in an area called the Jack Hills. The Jack Hills are 3.2 billion years old. They don't contain igneous rocks. They don't contain rocks produced by melts. They are sedimentary rocks. They are ancient river sediments that were eroded from mountain ranges that existed 3.2 billion years ago. The mountain ranges have all gone, at least they're not exposed at the surface anymore, but the sediments eroded from that ancient mountain range are still preserved in Australia. And in the sand, we find sand grains that are, of course, older than the sand itself. And some of these sand grains are made of zircon, zirconium silicate, which is a very useful mineral for geochronologists because it is very resistant to weathering and erosion. It is a time capsule of sorts that, once crystallized, is very robust to secondary alteration. The oldest zircon crystals that have been found in the Jack Hills are 4.3 billion years old. Again, it's a minimum age estimate, but it's the oldest materials that we know of on planet Earth. If you want to find older materials, still you need to go away from our planet, away from all the disruption that is caused by tectonics and by the fluid envelopes of our planet. So if we go to the moon, then we find older rocks than what we find on Earth. So on the moon, there are 2 types of rocks. We've got black areas. These are the mare, and we've got the lunar highlands, which are gray. The Americans have visited both of these areas in the 1970s, and they've retrieved materials from them and dated them. It turns out that the black areas consist of basalt and are considerably younger than the gray areas. The fact that they are younger is also quite evident from the fact that there are a lot fewer craters in the black mare areas than there are on the lunar highlands. So the lunar highlands have experienced meteorite impacts for much longer than the mare. Interestingly, the mare, which are 3.8 billion years old, the same age as the Isua complex in Greenland, I would like to add, they're only found on one side of the moon, on the near side. On the far side of the moon, we don't have these mare basalts. They have a circular shape, so they were formed by very large, late heavy bombardments of planetesimals that were hitting the moon. And we know that this dramatic event of impacts on the moon must have happened within a few days, because the moon didn't have a chance to rotate and expose both of its sides to this meteorite shower. The Earth, however, spins a lot faster, 28 times faster than the moon. So it is likely that during this event, the Earth was hit by lots of planetesimals, and its surface was completely reset by this late heavy bombardment. This may be one of the reasons why we don't have any rocks preserved older than 3.8 billion years on Earth. The lunar highlands were not affected by the late heavy bombardment, and its rocks have preserved a much older age of 4.4 billion years. So that's older than the Jack Hill's zircons, but it's still a minimum age estimate for our solar system. There are even older materials that have been studied by geochronologists. Meteorites. Meteorites come in many sizes, shapes, and forms. There are two dominant types of meteorites. There are iron meteorites, which are made of iron and nickel, and there are stony meteorites, the most primitive of which are called chondritic meteorites. These chondritic meteorites consist of small droplets of material that is postulated to have condensed out of the primitive molecular cloud from which the solar system formed. We know that it's very primitive because the metal composition of chondritic meteorites is identical to the metal composition of the sun, which we know from the spectrum of light emitted by the sun. So because the sun contains more than 90% of the mass of the solar system, it is representative for the composition of the solar system. The fact that these chondritic meteorites have the same composition is really telling us that it's a very primitive material. It's also the oldest material that has been dated to 4.57 billion years. So that is now generally accepted as the age of our solar system and therefore of our planet. All right, let's move on from uranium lead to a second chronometer, the potassium-argon system. Potassium has three isotopes, 39, 41, and 40. 40 is the rarest isotope. It is radioactive with a half-life of 1.25 billion years. So again, ideally suited for geochronology. Potassium is found in quite a wide range of minerals. It's quite an abundant element. It's also found in bananas. So bananas are radioactive. There is a unit of radioactivity, incidentally, called the banana equivalent dose, which you can look up on Wikipedia. Don't be afraid. The banana equivalent dose that would you need to ingest before it would kill you by radioactivity would be on the order of 100,000 bananas. So eating a banana is safe, but they are slightly radioactive because of potassium, which is decaying by electron capture and positron decay to argon 40, which is 1% of the air that we breathe. Now, the discovery of argon is actually an interesting story in which UCL played a key role. So I just want to digress a little bit and tell you a little bit about that discovery. So argon is a noble gas. It's found in the far right of the periodic table, but it was absent from the early drafts of the periodic table made by Dmitry Mendeleev. You can see here is a very early draft of the periodic table where Mendeleev didn't arrange the elements per column, but per row. So you can recognize lithium, sodium, potassium, rubidium, etc. Argon is absent from this table. In fact, all the noble gases, helium, krypton, xenon, and neon, are also absent from this table because these elements are all unknown to 19th century chemists because they are inert. They are very difficult to detect. The discovery of argon was triggered by some measurements made by Lord Rayleigh, who was setting out to measure the density of nitrogen, which is 80% of the air that we breathe. Rayleigh measured the density of nitrogen by producing nitrogen in two ways. His first approach was to apply chemical reactions to nitric oxide, nitrous oxide, and ammonia. So from these chemical reactions, he could produce nitrogen. And a second type of nitrogen, and the second approach to producing nitrogen was simply to remove all the oxygen from air and then consider the rest to be pure nitrogen. And he found that the atmospheric nitrogen was consistently more dense than the chemical nitrogen. And he postulated that this was due to the release of some light elements or molecules during these chemical reactions. He presented these results to the Royal Society in a meeting that was attended by UCL chemistry professor William Ramsey. And Ramsey thought that perhaps the cause of the discrepancy observed by Rayleigh was not the release of a light matter during the chemical reactions, but maybe there was something dense hiding in the air. So he then collaborated with Rayleigh, and together they applied some beautiful, elegant experiments to demonstrate that that was indeed the case, and that there is a new element, argon, that makes up about 1% of the air that we breathe. So this argon is 1% of the air that we breathe. Is all essentially produced by the radioactive decay in the Earth's crust of radioactive potassium-bearing minerals such as biotite, muscovite, feldspars, amphibals. Feldspar is the most common mineral at the surface of the Earth, so a lot of potassium is available, and a lot of argon is being produced that way, to the point where now 1% of the air that we breathe is that element. So that forms the basis of a geological clock. We can estimate time as a function of the ratio of argon to potassium in our potassium-bearing minerals. And that is a very popular method that has been used to date materials that do not contain uranium, which is often the case for volcanic ash layers, for example. And that has been really crucial in calibrating the geologic timescale and in dating the extinction of, species such as, animal groups such as the dinosaurs. So the dinosaurs existed or ruled the world between approximately 250 million and 66 million years ago, and then they abruptly disappeared. Dinosaur-bearing sediment deposits are found around the world and abruptly end and are overlain by sediments that do not contain any dinosaur fossils. It's a global event that is attributed to a large meteorite impact that happened at that time. The smoking gun for that meteorite impact is the existence of high concentrations of iridium on the boundary between the Cretaceous and the Paleogene eras. Iridium is a very rare element in terrestrial rocks, but it's very common in iron meteorites. So that's really a telltale sign that a meteorite had something to do with this. In the around 1980, don't remember the exact date, the impact location for that meteorite was found in Yucatan in Mexico, and within a few hundred kilometers of that area, tektites have been discovered. So these are droplets of molten rock that were ejected from the impact site. These tektites have been dated with the potassium argon method, and so have ash layers below and above the extinction layer. And that has allowed geochronologists to really pin down the extinction event to 66 million years, plus or minus 30,000 years, which is an amazing precision, a real triumph of high precision geochronology. All right, next one on my list is the uranium, thorium, helium method. I've already discussed the uranium lead clock, and I explained that when uranium decays to lead, it does so by emitting alpha particles, which when they acquire electrons, turn into helium atoms. So 8 helium atoms are produced for every lead 206 atoms. So we get another clock for free. Now, helium is a very different element from lead. You can see it's a much smaller element. It's a gas. It's a noble gas, also discovered by William Ramsey at UCL, winning him the 1905 Nobel Prize. Helium is not happy sitting in the crystal lattice of a uranium-bearing mineral, and at high temperatures will diffuse out of the crystal. It will move into the pore spaces between the crystals, make its way up into the atmosphere, and then escape to space, because the thermal velocity of helium exceeds the escape velocity of planet Earth. It is only when a rock cools below 60 or 70 degrees that the helium gets locked in and that the clock starts ticking. So unlike a uranium lead age, which is a crystallization age, the helium age is a cooling age. Now 60 or 70 degrees corresponds to a depth, we can remember from Lord Kelvin, of 2 to 3 kilometers. So a helium age tells us how long it takes for rocks to rise from those depths to the surface. So if you measure the helium age of the summit of Mount Everest, you will get an older age than the base of Mount Everest, because the summit has cooled before the base. I hope that makes sense. The age difference between the summit and the base tells us how rapidly the mountain is rising. This is called Thermo Chronology. It's an important branch of geochronology, important aspects of which were developed and continue to be developed at UCL. And then the final chronometer that I want to discuss, there are many more, but I'm just going to discuss 4, is the fission track method, which is based on this rare occasion in which a uranium-238 atom decays not to lead and helium, but by spontaneous disintegration into 2 particles of roughly equal size, krypton or barium, say, that release a lot of energy, move in opposite directions, and damage the crystal lattice in which they are hosted. So you can reveal these damage tracks, these fission tracks, by etching the uranium-bearing minerals, such as this apatite crystal, calcium phosphate crystal. You can etch it with acid and reveal these damage tracks. So each of these linear segments corresponds to a uranium atom that has disintegrated and damaged the crystal lattice. By counting the number of fission tracks per unit area, which you can do with an ordinary microscope, you don't need a fancy, expensive mass spectrometer for it. So by counting the number of fission tracks per unit area and pairing that with uranium measurements on the same crystals, we can calculate an age. And that age is similar in many ways to the helium age, because just like the helium method, also the fission track method is sensitive to temperature. When you heat a crystal to more than 100 degrees, the crystal lattice will heal itself. The tracks shorten and eventually disappear. It is only when the rock cools below 100 degrees or so that the fission tracks are retained and that the clock starts ticking. So again, this is a thermochronometer. Now, increasingly, geochronologists are combining all these methods. You can combine the uranium lead age to constrain the crystallization age of your rock. If you have potassium-bearing minerals in the same rock, then you can measure the potassium argon age. Argon is also a gas. The clock also leaks at high temperatures, but because argon is a bigger atom than helium, it will start ticking at higher temperatures than the helium. So it allows us to constrain how long ago a biotite-bearing rock, for example, cooled through 300 degrees. You can then measure fission tracks and constrain when the rock cooled through 100 degrees. You can measure the fission track lengths and further constrain the thermal history. You can measure the helium age and see when it cooled through 60 degrees. And because there is a one-to-one relationship between temperature and depth in the crust, this allows us, thanks to sophisticated computer programs, it allows us to track vertical motions in the Earth's crust and put first order constraints on plate tectonic processes over geologic time. So it allows us to track rock particles as they approach the surface, building mountain ranges, but it also allows us to then track how sediments that are eroded from these mountain ranges are buried in sedimentary basins, thick stacks of thousands of meters of sand and mud, which as they are buried get reheated and get reset. Fission tracks shorten, helium leaks. We can measure that in boreholes and quantify these geological processes in increasing detail. Now, this is just a small glimpse into the world of geochronology. The seeds for this whole field and the cradle of geochronology really is located in London. I already mentioned William Ramsey, the father of the noble gases, who really is who caused and is responsible for the eventual development of uranium, thorium, helium, and potassium argon dating. Robert Strutt was the son of Lord Rayleigh, Ramsey's collaborator, became a professor at Imperial College and carried out the first uranium, thorium, helium dates. Strutt's student, Arthur Holmes, carried out the first uranium lead dates in the 1920s. At the tender age of 23, he dated a Devonian rock from Norway at 340 million years. Really paradigm shifting stuff that gave us more reliable estimates for the age of the Earth. He published numerous books on the age of the Earth. And then Tony Herford was my predecessor at UCL. He's one of the founding fathers of modern fission track Thermo Chronology. So if you think of becoming geochronologist, London, I would tell you, is the place to come. All right, so that's the end of my main presentation. I would now like to conclude with a call for help. I am developing an app, a crowdsourcing app for fission track thermochronology, and I would like to now explain to you a little bit about this and invite you to take part in this crowdsourcing experiment. So as I explained, fission tracks is based on manual counts of fission tracks in etched grains, the number of tracks per unit area. Now, it's not always easy to tell which features on this grain are fission tracks and which are not. There are specks of dust, there may be crystal defects, scratches that may not so unequivocally be identified as fission tracks. Great progress has been made in recent years in automating the acquisition of fission track imagery using digital microscopes, and attempts have been made to automate the counting of fission tracks by artificial intelligence, but those efforts have had mixed and limited success because fission track counting is not so easy. So I was thinking to make progress in this field, make fission tracks analysis more accurate by crowdsourcing, which is an idea that is due to Francis Galton, one of the founding fathers of the field of statistics, who at the turn of the last century attended a farmers' fair in Cornwall, where 787 farmers guessed the weight of an ox. Whoever came closest, I guess, won the ox. Nobody got the right weight, but the average of the 787 estimates came within a pound of the true weight, which Galton referred to as the wisdom of crowds. A similar experience was evident from an experiment that took place in the second fission track workshop in Italy in 1984, where 22 analysts, some of which were just novice users, others were experienced fission trackers, 22 people were invited to count fission tracks in a sample of unknown age to them. Again, very few of the analysts got the right age, but the geometric mean of their estimates was spot on the 27 million year age of this Fish Canyon Tough age standard. So that gave me the idea to crowdsource fission track analysis. So I developed a website and an app called Geochron at Home, in which you can help counting fission tracks. And my hope is that by having multiple people count the same features, that we can increase the accuracy, but also increase the throughput of fission track thermochronology. Okay, so if you go to the Geochron at Home website, you can either try it without registering, but if you register, then that makes my life a little bit easier to keep track of the different people, fully anonymized and see and diagnose or identify whether there are any vandals in the system, for example. There is a tutorial which I would recommend you check out. Oh, my user interface has that suffered a little bit from the Zoom connection. I don't know why, but you can see that when you focus in and out of the crystals, you can see the grains in transmitted light and in reflected light. And I don't know. Ah, there we go. I think I know why. Okay, there we go. Very quickly, these are, I believe, fission tracks. They all have an etch pit at the surface, and as you are focusing into the grain, they've got a tail, which is this fission track. Now, some features I am not so sure about, and this is a subjectivity of fission track analysis. These features in these squares here, they all have etch pits, but they don't have a clearly recognizable tail. So I'm not sure whether these are fission tracks. You could count them or you could not count them. So as long as you are consistent with your approach to counting fission tracks, I compare samples to standards and I correct for this observer bias. And that's really the power of crowdsourcing. Some features like these are not fission tracks because they're all pointing in the same direction. Fission tracks should point in random directions. These are crystal defects. When a crystal is deformed under pressure, it can produce small cracks, which when etched out with acids can look like fission tracks, but they are not. This will confuse an artificial intelligence algorithm, but a human immediately spots that. And once you're done with the counting, you can, so let's see, you can count fission tracks by just, you can zoom in and out by clicking on the features. I think these are fission tracks. And I've got, let's say, 3 more here. If I make a mistake, I am able to correct that mistake by clicking on here and then 2 clicks on either side. Right? When I'm happy with my result, I submit result and you are presented with the next grain. So with that, I thank you in advance for your help.
I think all there is left is to just thank Pieter for the lovely talk.
It was a pleasure. Thanks for attending.
Yes.
Thanks for your questions.